So let's see the consequence of doing this. I have another code which just is a single block. Now we're only going to stick with quaternion because we know that the other representations have their own issues. So let's do okay, so this file will do linear interpolation as well as spherical interpolation. I just chose initial final time and initial angle final. I think there's a final angle somewhere, quat f, yeah. And then, okay, I'm going to show you a bunch of actually 4 different cases. First, we'll use LERP without any scaling. So this is just the linear interpolation. Okay. When I run this, it actually produces the quaternion dot, quaternion double dot. And actually do plots. But let me run this first so you see what you can expect. You're going to see 2 blocks. The initial position is this, and then the final position. So the light yellow is the initial position, the dark yellow or the opaque one is the final position. Okay, so that's that. And then this are some plots. Okay, there is a quaternion omega body. I'll show you how I get that. And then alpha is actually alpha body. Okay, so how do I get these two? As I said earlier, you can compute omega if you know q and q dot by using this formula, omega body using this formula. Similarly, if you take the derivative of omega b, you get acceleration using this formula. Okay, so these are all available because you know what the quaternion dot is. So what I did was, just to make it easy, I have a function over here which takes in inputs of, that's actually world free. Okay, you can do both. I have a function in the utility which does both. It converts the, if you give it quat and quat dot, it will convert that to angular velocity in whichever frame you want. Body frame, then use this function. World frame, use world frame function. Acceleration too. Okay, so once you get that, you can store it, which is stored here, and then the plotting is here. So I should change that name because this name is not really body. You could do any angular velocity because now you have these functions which will do it. So this functions basically take care of these formulas. It just does that once and for all, and that way you don't have to worry about that. Let's look at that plot again. I'm going to run this code again. What is of interest now is the angular velocity. I said when you use the linear interpolation, the angular velocity, no matter which frame, is non-constant, and you'll see this in one of those plots. Okay, so you can see that the angular velocity is not constant, even though the quaternion is linearly interpolated. This is a problem, right? Because your end effector is going to go at a non-constant speed. So what we'll do is, to fix this, we'll use SLERP. So here is the same interpolation done with SLERP. So I've written a function SLERP, which you can see. You will not see much difference in the movement, at least not to the eye, but the plots will show a different story, especially the one for angular velocity. So this one, the omega now is constant by using SLERP. And that's what you want. You want the end effector to move at a constant speed.
What? Alpha is always constant.
Alpha is always constant because you can look from the expression. Yeah. Okay, so this is the linear interpolation, but then I also did the scaling, which is using this expression. So what you do is you take this expression, you put it here, you take, you compute QLERP, you take the derivative of this. So it'll be 0 minus S dot T prime QI plus S dot T QF, and then take the second derivative. So you'll get quat dot and quat double dot, and those dot double dot can be used with the angular velocity formula. So here is the same thing done with LERP scaling. So it's basically using the same S of t in LERP. It actually does a pretty good job of ensuring that it gives you the velocity you want. So that won't change much. But if you look at the the angular speed and angular acceleration, you'll get what you wanted, which is for omega, we wanted omega to be 0 at the ends and it to be this way because that's how we chose it to be. It does that. And then if you look at angular acceleration, it starts and ends at 0. Of course, it goes back and forth, but that's what we designed the trajectory to be. And the quaternion is nothing different, it's the same one. Okay, and then you could also try this. I also did the same thing with SLERP scaling. There won't be much difference in this animation, but there will be a difference in the, well, it will be almost similar to LERP actually in terms of angular velocity and angular acceleration. Okay, here it is. Omega, you get a different response compared to that one. Okay. And then remember, this one also interpolates on that geodesic on the curve. You don't have to hack it and take the norm equal to 1.